All right, the last branch of the immune system is cellular immunity, which is part of the specific or adaptive immune system. So there's three main types of T cells that are responsible for cellular immunity. Helper T cells are not just part of cellular immunity, though. They actually are the central cell for your entire immune system. They help activate both humoral immunity and cellular immunity, so they are critically important for your entire adaptive immune system. Helper T cells are also called CD4 cells. Cytotoxic T cells, they are what the name suggests they are. So cyto means cell, toxic means toxic, and so these are toxic to cells. They are also known as CD8 cells. I tend to call CD8 cells assassins because that's how they work. They are going to run up to your cells that are doing bad things, and they are going to murder those cells that are doing bad things. So that's why they're assassins. Memory T cells work similarly to memory B cells in that they are long-lived. The difference is they're not going to differentiate into plasma cells. Once they re-meet their pathogen, they're going to differentiate into cytotoxic T cells. So they stay T cells. You can't turn from a T cell to a B cell, if that makes any sense. And of course, now my thing doesn't want to click. There we go. Clonal selection works relatively similarly to clonal selection back in the world of B cells. We still have to accept an antigen challenge. The difference is in how we're going to bind to the antigen. Here we're going to be talking about what I like to consider a flagpole flag sort of a situation, and we're going to have to come back to these MHC proteins that we had started with earlier. So MHCs, if you remember, were major histocompatibility complexes. They were the things on your cells that marked your cells as yours. Those are what I'm going to consider the flagpoles. What will happen is if your cells are doing bad things, they're going to run bad flags up the flagpole. And your T cells need to recognize two things, the flagpole and the flag. So we're going to have to do a co-recognition sort of a thing as we're going through here. So that's why we have to do a double recognition. We have to recognize both the flagpole and the flag and not just the antigen. So the class 1 versus class 2 MHC proteins are going to, 1, display on different types of cells, and 2, they're going to call to different types of cells. So your class 1 are going to be your standard MHC proteins that are found on most of the cells of your body. They're not on red blood cells, however. These are the ones that are going to call to cytotoxic T cells. So when almost any cell in your body is doing something it should not be doing, pardon me, like it's becoming cancerous, or it's been infected by a bacterium, or it's been infected by a virus, it starts to run bad things up its flagpole to tell a cytotoxic T cell, I'm your cell, but I'm not doing what I'm supposed to be doing anymore. And at that point, the cytotoxic T cell is going to murder your cell. Class 2 MHC proteins, on the other hand, don't talk to cytotoxic T cells, and they are going to talk to helper T cells. The reason for that is they're not on every cell in your body. They're going to be on your antigen presenting cells. Remember, those are your macrophages or your dendritic cells. Now, what you need to remember is those cells are supposed to run out and find bad things. So we don't want to destroy them for running bad things up the flagpole, because that's their job. So we don't want to kill them for doing their job. So they're going to run bad things up their flagpole, but their flagpole is a class 2 flagpole, and now it's going to tell a helper T cell, hey, I found a bad thing, please do something about it. Not, hey, I'm doing a bad thing, please murder me. So that's why we've got these two different MHC proteins. It's because in one case, we're doing something bad, and in another case, I found something bad. So, next up, T cells. You have what are the 2 steps required to activate a T cell. Since these cells are literally going to be murdering your cells, we want to regulate when they're doing that and when they're not. And so we're going to have 2 steps to activate them instead of just 1. We're not just going to be relying on antigen binding. So we are still going to do antigen binding, but then we're going to have co-stimulation after that. So, let's see, am I saying any of that on this slide? Blah, blah, blah. Okay, I already talked about the flagpole-flag combinations. These are the pictures from your book that are just showing you the class 1 MHC proteins. And so this is the MHC protein that's found on almost all of the cells of your body. So this is just, again, going to tell a cytotoxic T cell, hey, I'm one of your cells. If this cell's doing what it's supposed to do, it's going to run up a flag that belongs to your cell, and the cytotoxic T cell will come up and it'll check and it'll say, hey, I'm one of your cells, I'm doing what I'm supposed to do. So the cytotoxic T cell will come and say, cool, you're being good, and it will leave it alone. If, on the other hand, we have an antigen that is present, which means a bad guy, we're going to run the antigen up the flagpole, and now if a cytotoxic T cell comes in, we're going to recognize that this cell is yours, but it's doing bad things, and so at that point, we become a murderous little cytotoxic T cell. Flip side of that, class 2 MHC proteins, which are on our phagocytes. So again, they found a bad thing. They're not doing bad things. So we don't want to be murdered for doing our job. So we run that up a class 2 flagpole. So a helper T cell will see, I'm your cell that found something bad. Please go turn on immunity, not please destroy me. So that's the pictures from your book explaining what I just talked about. Okay, so 2 steps required for activating a T cell. Getting back to that. Step 1 is antigen binding. This works kind of the same. This is still sort of a come at me bro situation, except the challenge is coming from the flagpole flag combination. So if we're doing this from a class 1 MHC, which is how we have to do it, essentially, if we're trying to activate a cytotoxic T cell, we're going to have an antigen bound to the class 1 protein. The cytotoxic T cell is going to come up to that, and it's going to notice that 1, I have bound to one of your cells, and 2, that cell has an antigen that is not supposed to be there in it. That is the antigen binding that is going to turn on your T cell. Now, I like the analogy that your book uses here. At the very bottom, it says that once we do this, your T cell is turned on, but it's idling. So think of it like a car that you've turned on, but you haven't put it into gear yet. You're just sitting there, the radio is running, but you're not actually moving anywhere just yet. So that's what's happened after antigen binding. Now, in order for us to actually put the car in gear, we have to do co-stimulation. And this is going to involve a class of chemicals called cytokines. In addition to promoting inflammation that we talked about earlier, cytokines also stimulate our cytotoxic T cells to release their poisons that are going to kill your cells. It will also help stimulate proliferation so we can make our army of T cells. So not only does it help promote the killing action, it helps promote the enlistment of more T cells, if you will. In order for our T cells to actually work, both of those 2 steps have to happen. We have to bind to a flagpole flag combination, and we have to co-stimulate with cytokines. If we do both of those, we'll mount an army. We'll start poisoning your cells that are doing bad things. If both of those 2 things do not happen, your T cells will not actually mount an army, and you will not get better or become immune to whatever is happening to you. Okay. How do cytotoxic T cells deliver a lethal hit? So essentially, it's a poison game. When we poison, we're going to poison with enzymes. So enzymes, if you remember, they are proteins that help speed up chemical reactions. In this case, they're going to be digestive enzymes. Granzymes are enzymes that help break down both proteins and nucleic acids. So we are literally going to digest the DNA present inside the cell and all the proteins inside the cell that we're trying to murder. And then the first one that we actually release is perforin, and I'm hoping that name helps you realize what it's going to do. Perforin pokes holes in the cell membrane or perforates the cell membrane. So in this picture, let me get to my doodles. This big old cell is a cytotoxic, pardon me, no it's not, it's a cancer cell. It's even labeled cancer cell. This cytotoxic T cell would have bumped up against it and checked the flagpole flag combination and realized that this cell belongs to the body, but it's cancerous. It is doing things it is not supposed to be doing. Once it did that, this cancer cell also would be releasing the cytokines to co-stimulate, and so the cytotoxic T cell is going to release perforins, and you can see the holes that are developing in the membrane of this cancerous cell. Those holes are entry points for the granzymes, so the granzymes are going to go in there and then start poisoning and killing the inside of that cell as well. So here's the book's picture of sort of that process. So the perforins poke holes, and then the granzymes get in to start breaking down the DNA inside the cell. That's how they work. Let's see if this video will play. Let me see. I got to get my arrow back. Ooh, hey, looky there. Don't you love when you start playing with new things? I didn't even know that was a possibility. Sorry, guys. I get, again, easily amused. It is not that hard. Okay. So, engineered T cells are one of our newer treatment options that can be used to help people who have cancer. And so these have been engineered. That's what they mean. We usually take them out of a person and then we engineer them to fight a particular type of cancer, and then we re-inject them back into the person. And so notice the T cells are the little bitty cells. Here's a cancer cell, and then the T cell just pops it. I'll play it again just so you can see it. So you can see the docking and the checking happening on that middle one, and it'll play it one more time so you can see it. It's a beautiful thing when it happens. So that is how we actually use your immune system to help you beat cancer. It's called immunotherapy, and it's one of our newer techniques to help people who have cancer. And it's a wonderful new tool in our toolbox to help with that, and it relies on how your body naturally works. We just try to ramp it up and get you an army that much better, essentially. Okay. There's a lovely little table, 21.4, that kind of tells you what all the different cells do in your body. I have not talked about all of these. Now that I know there's a highlighter thing, let's play with the highlighter. We talked about B cells. They can differentiate into plasma cells and then memory B cells. We talked about helper T cells, CD4 cells, and then cytotoxic T cells, CD8 cells. We talked about the memory cells, both B and T cells. We talked about antigen presenting cells, which would be your macrophages, your dendritic cells. Now, regulatory T cells are important. We are really just in the last 10, 20 years starting to get a lot of good research on those. What those do is help prevent overstimulation of T cells so that we don't progress into autoimmunity. But again, we've really only been studying those for a little bit, and so we're trying to learn more about those, and so I don't talk about those a lot just yet, but they are important. We talked about antibodies. The other name is immunoglobulin, that have their plan of action. We talked about perforins and granzymes, that are how cytotoxic T cells actually murder your cells. We very briefly talked about the complement system, which is one of the ways that antibodies help to take care of your problem. Remember that complement is necessary for antibodies to carry out cell lysis. Antigen is always just the bad guy. We talked about interferons when we were talking about viruses. At least I think we did. Now I'm for some reason questioning myself. But interferons help a virus-infected cell protect a neighbor so that the neighbor does not also become viral infected. Interleukins, those help stimulate leukopoiesis, so you make more white blood cells. This picture used to be in the textbook. It is not in there anymore. I like this picture because it shows you your entire adaptive immune response and what happens. So let me kind of run you through it. So let's say that you get exposed to E. coli because you ate some spinach that some cow pooped on, because that's essentially what happens. So you get your E. coli. The E. coli goes into your digestive system, you absorb it. It meets a macrophage, which is an antigen presenting cell. The macrophage is going to run some of the E. coli up its class 2 MHC proteins, and then it's going to tell a helper T cell, hey, I met some E. coli, could you please do something about that? The helper T cell, which I told you is the central cell in immunity, here's why it is. What a helper T cell does is it stimulates B cells to make their clone army, so that you're going to make plasma cells, which will make antibodies, which, yes, that is spelled wrong. I did not make this picture. Helper T cells are also going to stimulate proliferation of cytotoxic T cells so that you can poison any cell that's not an antigen presenting cell that has let E. coli into it. It will, and by it I mean your helper T cells, will also help you make more memory cells, both memory B cells and memory T cells, so that you will have your memory cells for the next time you meet your E. coli. and you will not even remember if you meet E. coli again, because your secondary response will be faster, stronger, better. So that's what that picture is trying to show you. I hope that helps it clear sort of things up. I know that we always have to talk about things one at a time, but in reality, pardon me, both of these are happening together. All right. Now from there, oh, I haven't turned the page for a while in my notes, sorry. 4 graft types is the next thing that you guys have. The definitions are pretty easy for you guys to find, so I'm going to just kind of blow past those fairly quickly. The graft type most commonly used is the allograft, because most people don't have an identical twin handy, and you guys don't have a spare heart that we can just transfer in should you need one. So we have to get it from a person who is recently deceased most of the time. The problem with using an allograft is that nobody else on the planet has your same MHC proteins. There are people that have similar ones, but there's nobody who has the exact same ones. So if we give you somebody else's tissues, it's going to have a different flagpole on it. If a cytotoxic T cell runs up to that tissue, it's going to recognize that that is not your tissue. So when it runs up to the flagpole, it knows this is not mine. When it sees bad flagpole, that's an automatic, we need to murder this, it is not supposed to be here situation. So organ rejection happens because MHC proteins are not matching up, so the flagpole is not matching up essentially. So what we do for people who have had organ transplants is we put them on immunosuppressants. Immunosuppressants reduce the risk that they're going to reject the organ, but the problem with that is they do what the name says. It reduces their immune response. And so if they get the flu or COVID, it can kill them. So we have to fine tune the balance between suppressing their immune system just enough that they don't reject the tissue, but not so much that they die of the common cold when it happens to come through town. And that's a very fine balance. Now usually in class I show a particular video here, but if I linked to it in this video would end up getting blocked on YouTube. So I'm going to just link to that video separately. It's of the actress Sarah Hyland, who was in Modern Family, talking about her kidney transplants that she has had, and she has had multiple at this point. I think she does a really good job of sort of showing the emotional toll of organ transplants and explaining risk of rejection and what happens when rejection occurs, because it has happened to her. And so if you get a chance, watch that video. Okay. Immunodeficiencies are exactly what the name suggests. SCID is severe combined immunodeficiency. It's a genetic disorder where a person's immune system never develops because they don't have the genes for making their immune system develop correctly. If you've ever heard of bubble boy, there's not just one bubble boy. There's a whole slew of people who have it, but it is a sex-linked condition, so it is more likely to occur in males than females, which is why you very rarely hear of bubble girls, as it were. Gene therapy has been tried on SCID. It has so far been a mixed bag in terms of working. AIDS is also an immunodeficiency, but it is acquired, not genetic, which means you caught it. One of the things that I like to stress is not everybody catches it through sex, drugs, and rock and roll, essentially. There are a lot of people out there who have AIDS because of blood transfusions. Back in the day, before we really knew what AIDS or HIV was, there were a lot of people who got it because we weren't testing blood supplies for it, and so they got it through blood transfusions. There are a lot of people who got it through organ transplants. And so don't assume that everybody who has AIDS that you might be treating got it because they injected drugs that they shouldn't have, or they had sex with somebody and they weren't protecting themselves or whatever. Not that I'm saying be mean to those who did it wrong, but I'm just saying, again, be nice, essentially. This shows you the prevalence of people who have HIV in different countries, and notice the United States is not doing super well in terms of prevalence. Not as bad as sub-Saharan Africa where the disease originated, but we're still not doing awesome. America chose to not educate the population when we first discovered the disease, and unfortunately that was because the disease first showed up in the gay population, and the president at the time, Ronald Reagan, decided to tell his Surgeon General not to educate, because what was the big deal with letting the gay population die out? So we didn't really start educating for several years after, when we realized, oh, it doesn't just kill gay people. So we sort of screwed the pooch on that one. At this point, AIDS is not the death sentence that it once was. We have highly active antiretroviral therapy, or HAART, that can keep people alive and with HIV at nearly undetectable levels in the bloodstream for the rest of their lives. We can also, with HAART, keep their viral levels so low that they will not transmit HIV to their partners. With HAART, we can also have moms who get pregnant and they do not transmit the virus to their babies. And so again, there are people who are living with HIV who are having fairly normal lives. So it's not as bad as it was back in the 80s and the early 90s. That said, I do like to share that HIV is still something that is on the rise. Texas Department of Health changed the way they did the maps a while back, which makes me sad. I liked the way they used to do the maps. In the top 2 maps, each little red dot was a person who was diagnosed with HIV. It is a reportable disease. We have to report it to the TDH, who then reports it to the CDC. Notice the sheer number of red dots that increases between 1992 and then 2004 off over here. This map, let's see, it's from 2015. That was the most recent time that I pulled it from. And like I said, they stopped making the map the same way, but per 100,000 of the population, this shows you about how many people actually have it. I think they had to stop doing it with the red dots because there were so many red dots they couldn't fit it into the counties anymore. But I don't know, whatever. What I always just kind of like to show you is we are here in this county because I'm at the Cleburne campus and I usually teach at the Cleburne campus. I always forget which way Hillsboro is from there. I think it's south. Is it this way? If you're in Hillsboro, I think you're down there, but you might be down there. Sorry, I really suck at Hillsboro. That's totally my bad. That's Tarrant County. That's Dallas. Hood County, if you're a Granbury-ish person. There's Glen Rose, which is Somerville County, I think. So notice there's HIV in all of those counties, and it gets higher the closer you are to a metropolitan area. And not just higher because there's more people, it's higher per capita in those areas. And so essentially it's here, make sure you are having protected sex if you do not have a monogamous partner in your life. Okay, autoimmune diseases we have talked about before, so I'm basically going to bust past those, but make sure you get your examples that are in there. Let's see, hypersensitivities are allergies. Allergies are especially bad in industrialized countries, and what I want to stress is we don't really know for sure exactly why that is. I tend to believe in what is known as the hygiene hypothesis, which is essentially in industrialized countries we have kept ourselves so clean that we have not given our immune systems enough to do. And so the cells have essentially gotten bored and they are deciding to start damaging things because they have nothing else to do. Because people that do not live in industrialized countries don't have those same hypersensitivities or allergies. So that's one of the reasons why I sort of believe in the hygiene hypothesis, but I'm going to give you another example in a slightly later thing. Hypersensitivities are divided into 2 categories, and the treatment varies depending on which category it is because the cause varies. So immediate hypersensitivities are caused by histamine, which means they are treated with antihistamines. Now, anaphylactic shock is a severe immediate hypersensitivity. It is not just treated with antihistamines. It is treated with epi so that we can get blood pressure up, and then antihistamines are also onboarded to help. Delayed hypersensitivities are different. That involves cytotoxic T cells instead of histamine, and those we suppress their response by suppressing the cytokines, and we suppress cytokines with steroids. And so think like prednisone, anything that starts with cortisone, cortisol, those can be used to treat with those. Okay, hygiene hypothesis has the other name of the overclean hypothesis. And so this is sort of showing you some of the risk factors / evidence that we have to help support the idea of those. And asthma is on the rise as well, and it is linked to this asthma. Allergy-induced asthma is linked to the histamine response, although steroids are also used to treat that. There is evidence that pets do help reduce the risk of allergies. That could be because people with pets tend to be outside more taking care of their pets. Or this is actually my son, and yeah, he fell asleep like that, which bravo to him, because I don't think I could do that. And I don't know if my dog looked happy or not in that picture. Y'all can try to tell me what you think my dog looks like. That was Dollar. Dollar was a good puppy. He is no longer with us anymore. But my son used to not have a problem with dogs because he slept with a dog in his bed ever since we had dogs. And so that was one thing that I could say maybe helped his asthma not be as bad as it could have possibly been. Now, going back to one of the reasons why I think the hygiene hypothesis, why I tend to believe in that as a hypothesis. My son is the one in the tie on the left in this picture. My parental strategy was I don't like stinky boys in my house, and so I made him take a shower every night. I say made him. He likes showering. Even after he's moved out, he still showers on the regular. He likes cleanliness and whatnot. He became sort of an indoor sort of a kid, nerdy, played on his Xbox, his PlayStation, and that sort of stuff. At the age of 2, he was diagnosed with asthma, again, allergy-induced asthma. He had eczema. He's kind of grown out of the eczema. The asthma has gotten worse after he moved out of my house and after he stopped being on the swim team. But that's been his sort of crux to bear, is allergies and asthma. But he didn't have injuries or whatever throughout life. Then the child on the right off over here. Now my highlighter doesn't want to work. This is my brother's son. They are about the same age, which they aren't in this picture, but my brother's strategy is entirely different. My brother does not care what his home smells like, and so his kids wouldn't take a bath until like there was a cloud. Like, remember in the Peanuts there was that kid who walked around with a cloud of dirt around them? Yeah, his kids, like, you could smell them 3 rooms away. There were times they smelled that bad. They would constantly have injuries and have to be taken to the ER because of whatever, and you can see the broken wrist here in this one. That said, because they were outside playing all the time, none of his kids have allergies. None of them have asthma. My brother and I, if you were to see us, you would know immediately that we were siblings. We have very similar genes in us, and yet our kids are vastly different, and it's because of our different parenting strategies, and my kid tended to be an indoor kid versus his kids were outdoor kids. So if I had it all to do it all over again, the reason why I'm telling you this is, if you want your kids to have a healthier immune system, the immune system works better when you challenge it when they're children. So let them go outside. Let them eat dirt. It has been shown in numerous studies that kids who spend more time outside have a stronger immune system and a lower risk of eczema and asthma and autoimmune diseases. And so that's why I wanted to share that story with you. Like, it's too late for my kid. I ruined him already. But maybe you guys are young and you can still save yours. That's the end of the immune system chapter. I hope you liked it. Good luck on your next test.